Feeling a little cooler though. I don't know what's going on, but okay, that's good. All right, let me get back to this slide if I can, and we will go from current slide. Okay, let's see if there are any announcements that I can think of. There's one, this is just sort of a minor one, but it will affect maybe just a little bit. On Tuesday of next week, I'm supposed to be on the Birmingham West Campus at 5:45, so I can stay and answer just a couple questions maybe at the after class, but not that many because I got to get over there. I'm supposed to meet someone there at 5:45. It was her choice, not mine, so I just have to do it. Let's see, is it Kayla? Yeah. Okay. And already got you. Okay, right. So, not a major announcement, just a little thing. Okay. Can't think of anything else. Okay, as far as what we're doing in here, do you have any questions on anything we've done so far? Okay, now before you leave today, if you haven't already picked up the Chapter 16 test, be sure you do that, because we're going to finish Chapter 16 today. Knock on wood. Okay. Well, what we've done so far in Chapter 16 is wave motion and sound, and basically we did a little bit of wave motion, and then we've looked mostly at sound waves in 6.3, let's see, turn all the way back. Okay, 6.1 is characteristics of waves, which we did at the very beginning. Then electromagnetic waves, 16.2, that was just very, very short. 16.3 was sound waves, 16.4 the Doppler effect. So now we're into resonance. What does resonance mean? Anyone know? Let me give you a couple of non-sound examples of resonance. Now, I bet you, if you haven't done it yourself, you've probably seen someone do it. Do you think you could push off a car? No, they're too heavy, right? But actually, you can, as long as it's not too big a car, and it's not got the brake on, and it's not in gear, it's in a neutral. And what you do, you start pushing, and then let it rock. And right when it's going back the other way, push again. In the same direction it's going, let it rock, then push again, just timing your push for when it's rocking forward. What you're doing is getting on the frequency, natural frequency of the car, and you're resonating with that frequency. That's called resonance. Okay? Now, you do the same thing pushing a kid in a swing. You don't push when the swing's coming up at you. You wait until it gets at the very peak, and right as it goes down, then you push it, and then the kid goes higher and higher, higher, or stop, And so that's resonance. You give the push at the time so you're in sync with the device that you're dealing with. Same thing happens with sound, okay? Have you ever been in the same room when someone was tuning a piano? Okay, or a guitar maybe? Okay, you have, say it with a guitar. If they can get it just right, you can hit whatever you're tuning with, and if you have the string just right, it'll start vibrating by itself. That's resonance. Now, most of the time we're not that precise, but it can happen that way, and that's what the folks that are really good about tuning a piano, they wait until when they strike the key and they have the tuning fork or whatever it is, they vibrate together at the same time. That is exactly what resonance is, and we'll see in your book there's a copy of that. So we start with the concept of natural frequency. Let me get my pen set up. Okay. Natural frequency. Now, natural frequency of an object, such as a tuning fork, is the frequency at which it vibrates when struck by another object, such as a rubber hammer or something like that. Okay? Natural frequency of the car is that frequency that you get on when you're pushing, or the swing, or whatever of that nature. Now, without going into too much detail, there was a bridge. Did I tell you about this Verrazano Narrow Bridge? Okay. It's, I think, in Oregon, wherever the Verrazano Narrows are. A bridge going from an island to the mainland in the state of Oregon, way up there. And they had designed this bridge to be a certain type of bridge. I don't know if it's a suspension bridge or some sort of bridge. They just designed it like they did any old bridge. Now, if you've ever been on the West Coast, you know the wind comes whipping off the Pacific Ocean, because in the Pacific, you got tens of thousands of miles of open ocean, with nothing to block it. So whatever the wind is doing is coming, and it's been coming that way for a long time, and you can build up some pretty strong winds. They call Chicago the Windy City because it's sitting on the lake. Which one is that? Huron, maybe? Or Lake Michigan, maybe? Maybe Michigan. I think so. But San Francisco, just about always the wind is blowing. Same thing with Seattle and Portland. Well, the Verrazano Narrows Bridge is right out there in the wind, and it blows at just about the same angle and distance and stuff just about all the time. Well, they built the bridge, and it hadn't been there long when they started having this very steady gust of wind, windy gusts that happened day after day after day, just happened to be on the natural frequency of the bridge. And when they blew, it just started the bridge rocking. And people that were driving on the bridge nicknamed it Galloping Gertie, because it really felt like it was moving with the wind. And it was. But then the wind picked up a little bit and hit the natural frequency big time, and that bridge started not just rocking, it was rocking and rolling and actually tore itself apart. Crashed. Cars went into the bay. I mean, it was awful, okay? And ever since then, civil engineers who design bridges, they take into account prevailing winds. Back then they didn't. They didn't think it was a big deal. Verrazano Narrows Bridge, that's because they were on the natural frequency. The wind just happened to get on that natural frequency of the bridge. Now, they say that, I've heard people talk about this, how if a cat is walking, how it has sort of a springy step, and a cat walking across something like a suspension bridge you'll see out in the wilderness sometime, and the cat walking across that will sometimes get the bridge going if it happens to hit on that frequency. And that can be scary. Now, dumb example here, my wife's brother has 3 kids. The oldest is a girl, then the boy, then the youngest boy. And all the time, the 2 older kids just used to pick on the younger boy mercilessly, okay? And he was never big enough, or so, and they were just always on him. But then they were out in the wilderness somewhere. The family was hiking, and it just happened to be the girl and the older boy were not too pleased with being on this flimsy little bridge that was going across this really deep chasm. And Josh had no problem with it. So he got on one end and started doing the bridge, and it started rocking and rolling. They were screaming bloody murder, hanging on for dear life, and he was laughing his head off at him. He finally got him back then. They said they were going to kill him when they got to the other end. Or please don't, we'll do whatever. But nothing worked. He just laughed. Never mind. That's enough on that. Now, they mention here the sounding board of a guitar is forced to vibrate at the same frequency as the strings of energy transferred from the strings to the sounding board. That's an example of forced vibration. And that's why some guitars and violins are much superior to others, because their shape, their hollowness, everything is just perfect for the prevalent frequencies through which they do. The Stradivarius violin, you may have heard of them, ancient, I mean hundreds of years old, and yet they're almost priceless on the market because they're such well made and have those natural frequencies that resonate so well. So resonance occurs, let me back off one. The sound waves, okay, I wish they had this on the slide, but they don't, I'm pretty sure. Let me go and check it. I'm going to have to undo all this. I'm pretty sure they don't have this on the slide. No, they don't. Yeah. Okay, I didn't think they did, but I just wanted to make sure. In your book, if you have your books, that page 443, an identical tuning forks with resonant air column, the sound waves coming from the left fork cause the right fork to vibrate. Now, what they've done here is these are in a box, and the box is right at the same dimensions of the frequencies of the fork, so that when you ting on that, the box sort of is like an amplifier, like a megaphone, sending this out, and the other box is the same way, receiving it, and it causes this one to vibrate. And that's technically how piano tuners and perhaps even guitar and other instrument tuners can do. If they have an exact frequency, and these tuning forks are very exact, say for middle C or whatever, and you do your string to it, and if it comes across, and sometimes people with good hearing, I never could do this. My mother could. She had a good ear for music. I could never do it, but they can hear when they're right on the frequency. You'll actually hear a little beat. They call it a beat frequency. It's right so close that you can hear it. Okay. Now, the next thing on the picture right below that, this only works, I think, with really good quality wine glasses. They need to be crystal, not just glass. Some of the really good glass might work as well. What you do is wet your finger and roll it around the glass, and you will hear it start going, it starts singing to you, and that's what they call it here, the singing wine glasses, because has to be a good crystal, and that crystal will resonate. All right. That's all they have, no questions, no examples. So let's move on to simple harmonic motion. Now this is a thing that just about all physicists, they live by this. So many things in physics operate on simple harmonic motion, on these principles of simple harmonic motion. Type of linear motion in which the acceleration of an object is directly proportional to its displacement from the equilibrium position. Now we saw that with Hooke's law, remember? Exactly Hooke's law. The force that's exerted is a direct proportion to how much the stretch is. If you have a spring, you stretch it a little bit, it pulls back a little bit. Stretch it more, it pulls back more. So it's the force is a direct, the acceleration of the object, which is the force, is directly proportional to the displacement from equilibrium position. Hooke's law. Goodness, it's hot in here. Okay. This is going back to some of the same terms we had earlier. What we have, and we're calling the amplitude, remember we talked about the amplitude of a wave, that's the maximum distance from equilibrium position. Maximum distance, amplitude. That is a displacement. The displacement of the object in simple harmonic motion is its distance from the equilibrium or rest position. Okay? And we don't have a slide of that, so let me get down some of these terms. This thing drives me nuts. How it always manages to get tied up on here, I don't know. Okay. So simple harmonic motion now, does one of those words seem like it doesn't fit if you're talking about springs? Do you think of all three of those words when you think of springs? You may think of none of them. Motion, of course, has to happen with springs. What's the one word that seems a little bizarre? Harmonic. What do you think of when you hear harmonic? Songs, yeah, harmony, singing in harmony. Someone singing bass, someone singing tenor, someone singing alto, someone singing soprano. You think of harmony, okay? Well, those are not that far apart. What we've just been talking about is tuning instruments, resonant frequency, pushing cars, resonant frequency. All that is harmony, doing things in harmony, okay? Simple harmonic motion. So yeah, it really does fit this concept, okay? Linear motion by which the acceleration of an object directly proportional to its displacement. Its displacement is the distance from equilibrium position or rest. So there's the next term, displacement. And that one is directly related to what we were calling amplitude. Okay, of the waves, of the vibration. The amplitude of the vibration is the maximum displacement, which is also, and now we're getting into, and let's go to this now. This is kind of awkward, but it's the only way I can do these things. Okay. Goodness, I'm burning up in here. Wish the AC would come back on. Okay. Here is the one illustration. It's a rather strange illustration, but still an illustration of simple harmonic motion that has nothing to do with springs or singing or anything else. Here's a person in the Ferris wheel, the chair of the Ferris wheel. Sun is coming from directly overhead, or let's imagine it is, okay? Now, if you look at the shadow of that person, he's the only one on the Ferris wheel. Lucky him, okay? And if you look at him, as the Ferris wheel is turning that way, then his shadow is going to go down here and here, reach the end here, and then come back, and reach the end here and come back, and just do this kind of motion, back and forth, back and forth. Nothing to do with a spring or anything else. That's simple harmonic motion. The earth moving around the sun. Same thing here, okay? The seasons, fall, winter, spring, and summer. Fall, winter, spring, simple harmonic motion. All those things are related. The tides, up and down, just about every 30 days, not quite 30 days, like 29 and a half or something like that. The tides move in just about simple harmonic motion. Okay? So lots of things in nature and everything else operate in this type of way. One other thing that does, okay, let's talk about a couple of other things. The amplitude is the of the vibration is the maximum distance from equilibrium or rest position. Now, what would be that for the Ferris wheel? What would be the rest position? They show here an A prime, a B prime, and a C prime. I don't know why they put primes over them. Oh, I guess it corresponds to A, B, and C. Okay. Here's a D prime for D, and I can't read that one. Whatever that is. Okay. What would be the equilibrium position, would you think? Pretty much straight up and down. That would be pretty close to, well, B prime wouldn't be it. I think 0 would be it. That would be exactly. So A prime is not quite at the amplitude. The amplitude would be out here at Q when he was right here. There he's moved in just a little bit. There would be equilibrium position. Here he's just past equilibrium position. Here it looks like he's right at the max. So that would be amplitude, the distance from center, maximum distance away from equilibrium position. Then he's coming back this way and goes, keep on going. Okay, so equilibrium here would probably be right here. Maybe that's what, no? I can't tell what that is. Oh, that's an E. That's E prime here. The maximum is right out here at the end. Okay, so the period, let's get that down. Got to get my color back. Okay, period. We had period before. Anyone remember what period is related to? Or the symbol for it or anything else? Capital T. Now, in other contexts in physics, that would be temperature. We're not dealing with temperature here. This capital T would be period. That is a time. That's why they use capital T. That would be the time that it took for it to go from one amplitude all the way down here, not stopping here, but coming back to that same original position. That would be the period. Or from equilibrium, probably would go this way first, this way, back here. Even though it crossed here before, it has to cross in the same direction. So it would go here, here. This is not a period, here to here. The first one would have been half a period. Or even from somewhere else, like B. Going B to C, passing B again, coming back here, and going back to B in the same direction it was going before. Any of those would define a period. The time that it takes. Now, do you remember this term? Frequency. We talked about this before, back in 16.1, I believe it was. What is frequency? Say again? 1 over the period. Okay? Not time, period. And it's per second. So, yeah, the unit is 1 over time. Okay? Frequency is 1 over the period. Actually, the period is the time per cycle. In other words, the time it takes for it to make one complete cycle. So frequency is cycles per time. Now, cycle isn't a unit, but sometimes you'll hear it called cycles per second, right? Something like that, cycles per second. Technically, the unit for it is, anyone remember this? Hertz. And the actual fundamental unit is 1 over second, or second to the minus 1. That's what a hertz is. What's left out there is cycles, cycles per second. Okay, that's frequency. All right. Now, another thing that follows this, I don't think we have a slide of it. No, we don't. And let's go back, sorry about this, to the other one. Okay, let me get my pen back. Okay, is a pendulum. What is a pendulum? Anyone know? Anyone know what a pendulum is? Think grandfather clock. That thing that swings from one side to the other. That's a pendulum. It's not the only one. There's many other kinds of pendula, but that is one. It consists of an object suspended so it swings freely back and forth about some pivot. Okay? And they say pendulums. I always think it was pendula, but whatever. Have been commonly used in clocks for many years. I would say many centuries probably. The motion of a pendulum, when the displacement is small, very closely approximates simple harmonic motion. 3 basic properties of a pendulum discovered by good old Galileo. Okay, number 1. The period is independent of the mass. The period, which is the time it takes to make one complete cycle, completely independent of the mass. Okay? You put a different mass on it, the pendulum keeps swinging just like it did before. Okay? Now, air resistance is more affected by the shape and size of the bob than it is by its mass. So there's another reason for that too. Now, number 2, the period is independent of the amplitude when the arc is small. The period independent of the amplitude, okay, when the arc is small. Now that's sort of a weasel word there. How small is small? That is when it's less than 10 degrees. Okay. Now there's a reason for that, but I think it's a little beyond the scope of this course to talk about it too much, but there is a reason for that. Now, subject to those two conditions, what does the period depend on? Strictly the length of the pendulum. That's it. It doesn't matter about the mass. It doesn't matter about the amplitude, as long as you keep it small. It does depend on the length. And here it is. T, that's the period, is equal to 2 pi. Good thing to have with simple harmonic motion. Think of going around in a circle, the Ferris wheel, 2 pi one time around, times the square root of the length of it over the acceleration due to gravity. Okay? Now, and you can do the length, if you're doing it in meters, the acceleration due to gravity would be 9.80 meters per second squared. If you're doing the length in feet, then it's 32.2 feet per second squared. You have to match the acceleration due to gravity with the unit you're dealing with in the length. Okay. I always like to check on the units to make sure they make sense. What should period be measured in? I almost gave it away. Second? Seconds. Okay. 2 pi is a pure number. There's no units associated with it. Okay. Now here under the square root, length, what unit would you use there? Meters or feet. So let's put meters to begin with. We could do the same thing with feet. Okay. And then if you use acceleration due to gravity, if you use meters for length, then you use 9.80 meters per second squared. If you use feet, you would use 32.2 feet per second squared. So whichever you use, the length unit is going to cancel out, and you have 1 over second squared, which would give you second squared. Square root of second squared is what? Square root of a perfect square? The square root wipes out the square, and you're left with second. Perfect unit. Perfect unit. Okay? So, it depends only on the length and the acceleration due to gravity. So if you happen to have a clock that's perfectly tuned on Earth, don't take it to the moon. It won't work well. Okay? Because it just won't. So there's only one example here. Let's do it. Okay? But keeping in mind what we just said. Find the length in centimeters. Looking for find the length in centimeters. Ooh, boo hiss. That means some unit conversion, doesn't it? Of a pendulum. By the way, what symbol will be for length in that last formula we had? L. That's just the L, length. Okay? I have a pendulum with a period of 1.50 seconds. By the way, a period, what's the symbol for period? Capital T of 1.50 seconds. Okay? What formula equation relates the period to the length? We just had it. Capital T is equal to 2 pi square root of L over G. Okay. Now, we got period, in units of seconds. We're looking for the length in units of centimeters. So either we do the problem with meters and then convert centimeters to meter, or we could convert our G in meters to G in centimeters. Which way you want to go?
The simplest.
Second?
Whatever the simplest.
I can't hear you.
I said whatever the simplest.
They're both about the same.
Mm-hmm.
So I'll let you choose.
Do the problem.
Huh?
Do the problem.
Do the problem in meters and then convert to centimeters. That sounds good to me. So here's T is equal to 2 pi. Okay, now, sorry, next question. Before I wrote that, I should have asked it. Do you want to solve for L first and then plug in the numbers, or do you want to plug in numbers and then solve for L? Solve for L first. So let's do that first. Oops, wrong thing. Okay, hit the wrong button here. So let me erase this. Okay, here we're trying to solve for L. Okay, there's the L. That's what we want to solve for. So what you reckon the first thing we need to do? Okay, pretty good, except not multiply, divide. We want this to get out of there because this is messing up the L. So let's divide both sides by 2 pi. Divide that by 2 pi, divide this by 2 pi. That wipes out your 2 pi, right? You could do 2 and then pi, but I'm just lazy. I'm going to do it both at once. Okay, so now what we have, I'm going to write it out. T over 2 pi is equal to the square root of L over G. Now, what you reckon we need to do next? Again, we're solving for the L. What's in the way? That square root symbol. How do you undo a square root? Second? You square both sides. Excellent. So this will be T squared over 4, because 2 squared is 4, pi squared is equal to, lose the square root over here, L over G. And now what do you do? Again, we're trying to solve for L. Yeah, got to get rid of the G, so multiply both sides by G. Done. So here we have L is equal to G T squared, I went to Georgia Tech, I like the sound of that, okay, over 4 pi squared. Okay? We know what G is in SI units. What would that be? 9.80, and that's meters per second squared. And then we were told what T is, 1.50 seconds, but we're going to square that, divided by 4 pi squared. Okay? I hope most of you have calculators with the pi key already on it. If you don't, you can use 3.1416. That'll give you more than enough precision. Okay? So let's socket to it. That would be 9.80 meters per second squared times, I'm pretty sure 1.5 squared is 2.25 seconds squared. Someone check me with your calculator, make sure I'm right there, over 4 pi squared. Okay? Now, we could have done all this just by typing in keystrokes, but now I don't see any advantages not to just pulling out a calculator. 9.8 times 2.25. By the way, notice the second squareds cancel out, and you're left with meters, and that's a good unit for the L, meters. Okay? Divided by 4, and then divide that by pi squared, which you'll need a calculator to determine that. Now, if you don't have the pi key on your calculator, use 3.1416. Square that. Anyone got an answer? 0.5585, and that would be meters. Okay? They asked for it in centimeters. So how do we get meters to be centimeters? Conversion factor, and you're trying to get to centimeters. So what do you put in place first? The units. Centimeters on top, meters on the bottom. How many centimeters in a meter, or how many meters in a centimeter? 100 centimeters makes exactly 1 meter. So there's your conversion. And really, when you multiply by 100, that's 2 zeros. Just move the decimal twice. That would be 55.9. Because they want 3 significant digits. Because you had 3 here, and we had 3 here, and we did our pi at least to 3 digits. You probably used better than that. So 55.9 centimeters. What did they get? 55.9 centimeters. Now they didn't show how to convert, they just moved the decimal 2 places. This shows you how to convert. That way, frankly, when I was grading a few of the papers, I could see some people went the wrong direction with decimals a time or two, okay? So be careful. Use your conversion factors to keep you from going the wrong way. All right, any questions? Okay, problem set 16.6, you could do any of the odds 1 through 13. I think those answers are in the back, most of them anyway. The glossary here, quite a glossary on this one. That's more than 1 page, and formulas, quite a listing of formulas here. They number 5, but a couple of them have more than 1 expression. Then there's review questions, which are nice, simple, multiple choice things, and then some that aren't multiple choice. You can answer those otherwise. But your review problems, these are the ones that would probably be more like your test questions, any of those odds 1 through 17. And then there's, oh, there it is. Look at that. The Tacoma, I may have said it wrong. Tacoma Narrows Bridge. There it is. They got a picture of it galloping like Gertie, okay, on page 450. I'd forgotten that picture was in here. Okay, so you can go with that. All right. That finishes chapter 16. And now we move to the next chapter, which is 17. But before we do, does everybody here get a copy of the test for 16? Any of you who did not? Okay. Let me get it for you. I thought maybe you got it class beforehand. If I gave some of it, it. Okay. You did? Huh? You did one. All right. And, okay. All right. Just set them down. Did you get? I thought you got that. Okay. Are you sure you didn't get that one?
I want to hear. I got this.
Yeah, I know. That's what I said. I gave it to you.
I thought you asked about
This is 16, isn't it?
Yeah. That's chapter 12.
Well, this is 12?
Yeah, you just gave me, I think, 12.
Oh, wait, yeah. This is 12. I'm sorry. I didn't go deep enough in my stuff. Sorry. I thought I was at the bottom, but I'm not. Okay, did I give anyone 16? I think I did. Yeah. Yeah. Yeah, I remember now. I remember I had 2 corrections on it, and I had 2 corrections on that one, but these were different. Okay, you didn't get that one. You didn't get that one. Okay, everybody else got that one. Yeah. First question is, what is the period? Then find the frequency, and then the speed. Okay, now for those, I just gave them to you. Let me remind you of this. Number 8 This is the sorriest test bank I think I've ever dealt with. A train traveling at a speed of 80 miles per hour approaches an observer at a station and sounds a whistle. What frequency will be heard by the observer? Well, you got to know the frequency of the whistle. They left that out. So the whistle is at 585 hertz, HZ.
You said this the frequency.
That's the frequency, 585 hertz. And then the question is, what frequency will be heard by the observer? Now, this is the one with the train approaching the observer. So you remember you have that formula, and you have to decide whether you use the plus or the minus sign. So go back and check on that. Assume the speed, sound velocity in air is 1,090 feet per second. Now, what do you notice a deal with this problem is? As with many of them. Units. The train is traveling at 80 miles per hour, but you have the sound velocity at 1,090 feet per second. So you either got to get the 80 miles per hour into so many feet per second, or you got to get the feet per second into so many miles per hour. It really doesn't matter which way you go. You just got to change one to the other. Okay? Now, question number 9, they got a little bit better, but still didn't get there. A car is traveling away from you. This one's going away from you at 70 miles per hour. The car horn produces a sound at a frequency of blank. They don't put it in there. They got the odd there, but they didn't put what it was. And that's 5,000 hertz, which is a pretty high frequency horn. 5,000 hertz. What frequency do you hear? Now the car is traveling away from you. Remember that one. So on that same formula, you have to use the other sign. One's a plus, one's a minus. Okay, and then the last, number 10, is the one we did today. Something similar to that. So everybody else did get a copy of this last test. Yay or nay? Yeah. Okay? All right. Good deal. Now, we're ready to start Chapter 17. Now, I'm trying to remember what sections we need to cover, because there's more sections here than we can possibly cover. I think what we cover, we start with 17.3. So basically, I'm going to hit the first of these really quickly, just so we'll all be on the same page, you might say, wavelength, you might say. Let's just go through very simple things with electricity. There is a basic unit of charge for electricity. That's the charge on a single electron, which is also the same charge as on a single proton, with one major exception: opposite sign. Proton we have designated to be negative. Electron designated negative, proton P, proton positive. Okay? Exactly the same amount of charge. Now, a proton is tiny, but it's, compared to an electron, enormously massive, like 10,000 times the mass of an electron. Electron, you can just barely measure its mass, and you can't really isolate it. No one's ever seen an electron. They see the path or something like that. It's so incredibly tiny, it almost seems like it's just the tiniest of particles with a charge. Whereas a proton is 10,000 times more massive, and yet it has the same charge, just with the opposite sign, positive sign. Then you have other objects in an atom that are called neutrons, which are same size as a proton, maybe just a slight bit bigger, but absolutely no charge whatsoever. None. Zero. Nada. Nil. Nothing. Okay. And here's where I thought, I've seen it in other places too. Benjamin Franklin first referred to the electric charges as being positive or negative. Now, I don't remember if he was also the one that designated which is which, but probably ever since then we've regretted how he chose them. Okay, and I'll tell you a reason for that a little bit later. But he first referred to those charges as positive or negative. The study of those charges by themselves is called electrostatics, because that static charge is not moving. Later, and this is what we'll focus on, is current electricity in which they are moving. Okay? Now, electrons also, well, not just electrons, materials, some of them conduct charges and some they don't conduct. So we have conductors or non-conductors. Okay? And without going into all the detail, by the way, Benjamin Franklin has his own little blurb over on page 453. It was mentioned on 452, but he has a little blurb there on 453. I mean, it has to be one of the most unique individuals of all time. He was a scientist, an engineer, a publisher, a statesman, a writer, I mean, he did it all. He was an ambassador. He was an incredible individual. How he wound up here in our country doing all this stuff, our good luck. Okay, induction. We're not going to go into much detail here. Induction is just the ability of materials to be influenced by charges. Let's just leave it like that and go on. You can read some of the things here. Here's a Van de Graaff generator, which you may have seen people play with before. You got a picture of people doing that, 3 kids doing it on page 455. We're not going to do that. You can play with some of the material if you want to. Let's move on to Coulomb's law. Okay? Now, I said the fundamental unit of charge is a single electron or a single proton. Electrons are a lot easier to isolate than protons, okay, generally. So that's the smallest. But you know, that's so submicroscopically small, no one really uses that much. To use something we can deal with on an everyday basis, much bigger than that, okay? And this charge on the proton or on an electron, the charge is usually called E positive for proton or E negative for an electron. Okay? That is that fundamental charge I was talking about before, a single electron. By the way, Robert Van de Graaff has a little blurb on the right-hand side of 455, and then Charles Coulomb does too. Okay? But in the study of electricity, because these are such incredibly tiny little units, in fact, you have a hard time measuring them, period, a much larger unit of charge is required, and it's called the Coulomb, named after Charles Coulomb. It's the measurement of the unit of charges, and this is how big it is. E plus, that's the charge on a single proton, is 1.60 times 10 to the minus 19 coulombs. Okay? That means it takes the reciprocal of that number of electrons to make 1 coulomb. But a coulomb is a good measurable unit, named after Charles Coulomb. And by the way, when a unit is named after a person, it's usually given a capital symbol. So capital C is Coulomb. That is the SI unit of charge. Okay? Now, E minus would then be minus 1.60 times 10 to the minus 19 coulombs. Same size exactly, just opposite signs. Positive for the proton, negative for the electron. Now, what that means, it would take 6.25 times 10 to the 18, if you can imagine that. Here's that number. 6, 250, 000, 00, 00, 3 zeros, 000, 00, 000. An enormously large number. Let's see, 3 zeros is thousands, 6 is millions, 9 is billions, 12 is trillions. This is a million trillions. I mean, it's an enormous, enormous number of electrons or protons, which do they say? Electrons, to make 1 coulomb. I'll just leave it capital C, because we already talked about that's the unit. I was going to spell it out, but we've already talked about that. Okay, I can't get my pen to come on. There it comes. Okay. Now, do you wonder how we came up with that number? If you'll punch in your calculator the first number, 1.60 EE or EXP -19, and then press the key x to the -1 or 1 over x, that key, you'll see something very close to this one come up. It's exactly the reciprocal of the other one. Okay. And that has, I said 1 coulomb, that's 1.00 coulombs, because you have 3 significant digits in both cases, so 1.00 coulombs. Now, that seems like a huge number. It is a huge number of electrons, but that's the number of charges that would go through a 100-watt bulb in 1 second. So it's a lot of charges, okay? That's 1 coulomb. Now, what Coulomb did, and by the way, notice the year, 1789. What was happening about 1789? Anyone remember? Second? Yeah, the U.S. was Declaration of Independence, as we learned yesterday, if you were listening to anything. 1776, we were fighting with the British at the time, and the French were helping us. Guess who was one of the early ambassadors of France? Benjamin Franklin. And you want to bet that scientist, when he got over to France, did not get in touch with Coulomb and some of these other French guys and get together and compare notes. I can't believe they didn't, okay? And they were both, like I said, I don't remember exactly when Franklin was the ambassador to France, but I know he held that position for some time, and I know he traveled to France, and I know that he must have gotten in touch with them. Now, by the way, what was happening in France shortly after our War of Independence? Let me phrase that differently. Our Revolutionary War. The French Revolution. Right about this time. And this was a terrible time to be in France. That was one bloody, awful revolution. Much worse than ours. Okay? But it was also a time of throwing out the old and starting with the new, so it probably was not a bad time for scientists to start doing a lot of other stuff, you know, looking at new things. So Coulomb made a scientific study of the forces of attraction and repulsion between charged objects using very sensitive torsion balance. From his experiments, he determined the existence of an inverse square law, which means if I have a positive charge here and another positive charge here, and they're this distance apart, they're going to be repelling each other with a certain force. If I double the distance, they still repel each other, but it's 1/4 the force that they had here. If I half the distance, rather than doubling the force, it quadruples the force. So it's an inverse square law. It's not just an inverse relationship is the inverse of the square. Okay. Now, here is his law of electrostatics. Again, charges by themselves, not moving. The force between 2-point charges, Q1 and Q2, so the force, and I'm going to call it, they don't call it, I call it electrostatic force. So I put a little E there. Is directly proportional, so I'm going to first use the proportionality symbol, directly proportional to the product of the charges, Q1 times Q2, and inversely proportional to the distance between them, the inverse square law over r squared. It needs to become an equal sign. You need a constant proportionality, and that becomes K. Now, that's everybody's favorite for a constant, K. But this K is called Coulomb's constant, okay? And Coulomb's constant, by the way, is 9.00 times 10 to the 9th, and this is Newton meter squared per Coulomb squared. Okay? Now, it seems like a weird unit, but it almost has to be that. Sorry. I sit too long, I get stiff. Okay? The K, since it's over here, it must have a Newton to balance that out. So there, sure enough, is a Newton. But it has a 1 over meter squared here, so it has to be a meter squared up here to cancel that out. And then this is a Coulomb, that's a Coulomb, multiplied here, so we have to divide it here to cancel out the Coulomb squared. Okay? So sure enough, that's the unit. Now, this is just a little side note. This formula looks much like the one it did for Newton's universal law of gravitation, which is F sub g, for gravity, is equal to a capital G, mass 1 times mass 2, rather than charge 1 by charge 2, divided by r squared. Okay? The difference is that G was an extremely tiny number, 10 to the minus 11. This is a huge number, 10 to the positive 9, which, now that, the units are different, so that accounts for some of it, but the rest of it, that's saying that the force of electrostatic attraction is actually stronger than that of gravity. I don't know if I buy that. The trouble is it doesn't extend as far. Gravity, we're under the influence of the sun, which is 93 million miles away, and we're still under the influence of that. We're the sun and our whole solar system under the influence of the center of the Milky Way galaxy, which is light years away. So gravity acts over very long distances, but actually electrostatic attraction is actually stronger. And here's how you can tell that. Have you ever seen this experiment? If you got clean, dry hair, it doesn't work if you're a little oily or damp hair or something like that. In fact, damp weather, it doesn't work very well either. But with clean, dry hair, you can brush or comb your hair with a nylon brush or comb, okay, and then hold it down near little pieces of paper, and you can actually see the paper jump up to the comb. The reason is the electrostatic attraction is stronger than the gravitational attraction, which would keep it on the table. This makes it jump up. So it's actually stronger, overcomes the force due to gravity. But not for very long. You hold it a foot above and it's not going to touch it. Okay. So, let's do example 1. Okay. Y'all got the formula? Okay. I'm going to have to erase it to have room to do this. 2 charges, each with a magnitude of 6.50 microcoulombs. So charge 1 is equal to charge 2, and these both are 6.50 microcoulombs. Now, does anyone remember what a micro is? Okay, if you've ever done any drug dosing, I take Synthroid, which is a thyroid supplement, you might say, and it's in micrograms, which was a milligram of a milligram, a milli of a milligram. It's a millionth. This is a millionth of a coulomb. So to write that in terms of coulombs, this is 6.50, I can't write, times 10 to the minus 6, that's millionth, coulombs, microcoulomb, okay? separated by a distance of 0.200 centimeters. So our R here is 0.200 centimeters. Uh-oh, SpaghettiOs. Our formula is in meters, right? That's what your unit is. Newton meter square per coulomb square. So we need to get that into meters. Anyone either know the answer or tell me how to get the answer? Multiply by what?
Multiply 2.00 times 10 to the
Negative what?
3.
Negative 3. That would be millimeters. Centi is 10 to the minus 2. So that, okay, so that would be 0.200 times 10 to the minus 2 meters. Centi is 100. Remember, cents in a dollar? 100. So you move it 2 places. Or you could have moved the decimal 2 places to the left. Because you're making a bigger number, you have to have a bigger unit, you have to have a smaller number. And that's indeed what you got here. Okay. Now, I think I know what you're saying, though, because that's a 2. If you move the decimal here 1 place, that makes a bigger number. You have to reduce that by 1. So that's the same as 2.00. This is what you were thinking, times 10 to the minus 3 meters. So if they had said, to begin with, rather than 0.200 centimeters, 2.00 millimeters, then you'd have gone right to that. Yeah. So this book just loves to find bizarre ways to express numbers just to make you go through the exercise of getting them right. Okay? 2 charges, each with magnitude of that, are separated by a distance of that. Find the force of repulsion between them. Since they're both positive charges, they're going to be repelled. So what is that force of repulsion? I call it F sub B. And what's that formula? K, Q1, Q2, divided by R squared. Our K was 9.00 times 10 to the 11th, I believe it was. No, 9th. I'm sorry, I was doing the other one. 10 to the 9th. It was Newton meter squared per coulomb squared. That's why we had to get to meters and coulombs. Times, where is it? There it is. 6.50 times 10 to the minus 6 coulombs times 6.50 times 10 to the minus 6 coulombs. They were each the same size, so that's that. Divided by your R, there's your R, 2.00 times 10 to the minus 3 meters squared. Okay. Now, say that one more time. 0 times 10 to the minus 3. That's what we got up here. Our R was this, as that was this. Okay? Now, I like to take care of units first because hauling around these are really hard. Okay? This has a meter squared. This has a meter squared. Now, remember, you got to square the number in that. Okay? This has a coulomb square, which is a coulomb times a coulomb, so those go out. So we're left with newtons, a great thing for a force to be. So if you got a calculator, 9 EE or EXP 9 times 6.5 EXP or EE negative 6 times 6.5 EE or EXP negative 6 divided by 2 EXP or EE negative 3, but then square the 2. So be sure you open up a parentheses before you do that 2 EE or EXP negative 3 in parentheses, and then square it before you hit equal. Hopefully your calculator will do the math right. Now what you can do if you don't trust your calculator is do that first, and I can do that one. That would be 4.00 EE or EXP negative 6. You square the number before the exponent, you double the exponent. So if you want to just put that number in, that would be an easy way to do it. Okay? Don't have to trust your calculator. 9.00 times 10 to the 9th. I'll just put Newton because I got rid of the others. Times 6.50. You don't have to put the 0. Times 10 to the minus 6. I already wiped out the coulombs. 6.50 times 10 to the minus 6. We wiped out that one too. Divide that by 4.00 times 10 to the minus 6. When you square an exponent, you're doubling the exponent. When you square the number, you square the number. Okay? So that should give it to you. And by the way, just looking at this, 10 to the minus 6 will cancel one of those out. And it looks like you're going to have something about, oh man, 10 to the 3rd or maybe even 10 to the 4th. Is that right? That's an awfully big number. 10 to the 4th. That's right. Someone do that on the calculator? And guess what, folks? As you see from these examples, you're going to need to know that scientific notation. Be able to use it well. Here's the thing I can't believe. This book is in the 11th edition, and we're still finding all those errors in the test bank. It's just, evidently, they haven't done much. Either they've come up with new questions, they haven't checked them, or they never pay any attention to them. I don't know which. Anyone got an answer yet?
So the way I did, I multiplied the top numbers. I got 0.38025. And then, I guess just the steps that I did. Then I multiplied. I did the square. I did the 2.00 times 10 to the negative 3.
And then you squared it.
Squared it. So I got 95062.5.
9506. Say again.
95062.5.
Okay. Now, let's move that 4 digits this way, and that would be 9.5 with. Everything here has 3 digits in it, right? Okay, everything has 3 digits. Okay, so let's just do 3 digits. Look to the right. That's a 6. That's more than 5, so make that a 1. Times 10, we move that 4 places, 10 to the 4th, and that would be newtons. And that's exactly what they got, which to me is a pretty large force. Okay, so they are really pushing against each other. So that's problem set 17.3. You can do any of the odds 1 through 7. Okay? Any questions? Okay. All right. Okay. Okay. Any questions? All right. Let's get started on 17.4. 17.4, you need me to leave this up a little longer, or are we okay? Need it? Okay. So let me clear this out of the way. 17.4, the title of it is Electric Fields. If you build it, they will come. No, that's a different thing. That's Field of Dreams. Okay, in terms of static electricity, an electric field exists where an electric force that we just had with Coulomb's law of attraction or repulsion acts on a charge brought into the area. Okay? Now, this whole concept, there's two types of forces. I push on the chair and I move the chair. That's called the contact force. Okay? Now, you may have read or heard people talk about telepathy. Can I move that by thinking? No, I can't. Okay? But that would be a force at a distance. And people have puzzled how in the world these forces at a distance work. But you know they do. The sun is 93 million miles away and it pulls the earth toward it all the time. That's why we go around in a big ellipse. Okay? It just happens. Okay? And that also is what happens. Let's say we have a charge here. You want it to be positive or negative? I don't care. Positive. So there's some nice old positive charge here. Okay? Somewhere way out there we have another little bitty charge. What you want it to be? Negative. Okay. Now if it's far enough out there and small enough, that one probably isn't going to act too much on it. But if you bring it in closer, after a while it's feeling that charge, it goes flying toward it, picking up speed as it goes, because the closer it gets, the stronger the force. So that is a field. There's no touching of this to that, but it's being attracted by a field. Okay? The force is exerted over a distance, and that is what we call the electric field. It exists when an electric force of attraction or repulsion acts on a charge brought into the area. Okay? And they show the picture here. If you take that balloon, I think probably rub it on your hair really, if you have enough hair, I don't, so really hard and stuff, and you can stick it to the wall. Okay? It'll stick on the wall. A balloon wouldn't normally stick on the wall, but it would, because you've probably rubbed electrons off your hair onto the balloon. Now it's charged, the wall is neutral, so they stick. Okay. I don't know why they put wall there, because it's fine. That's a force at not very great distance. So if you deal with it, if you think of this, that Coulomb's law, electrostatic force, is K Q1 Q2 over R squared. Okay, the distance between them. What the field is the force per unit charge. So take one of those charges and divide it here, and you get the force. I've said it backwards. Okay? Sorry about that. If I get my eraser to do. Okay. Okay. Take the force and divide it by a charge. They call it Q prime. And that actually is going to be your test charge. So it will do Q1 Q prime. So divide this by Q prime, and this gives you the field. Electric field is force per unit charge, and that would then be, the electric field is K, that same Coulomb's constant, Q1, that's the charge that you had up here, over R squared. It's not a force between two charges, it's the field that this charge exerts on any charge coming in. Okay? That charge coming in would be your Q prime. Okay. And that is a vector quantity, because forces are vectors. Charges are scalars. They don't have direction. Okay? But so a field is also going to be a vector. It has both magnitude and direction. Okay. Let's try to do example 1 and see what we can do. A positive test charge of 30 microcoulombs. So this is our Q prime, is 30.0 microcoulombs, which is how another way to write that, not using a symbol. 30.0 times 10 to the micro, help me, -6 coulombs. But that's not really in scientific notation, so I'm going to move this decimal one place to the left, making a smaller number. So that's going to be a bigger, if you make a smaller number here, you have to make a bigger number there. So that would be 3.00 times 10 to the, make that a bigger number by one place, and that's -5th. With negative numbers, you know, go the other way. Coulombs. Okay, so there's your test charge. Okay? A positive test charge of 30 microcoulombs is placed on an electric field. The force on it is 6.6 newtons. So that's your F sub E. Electrostatic force is 0.600 newtons. Okay? What is the magnitude of the electric field at the location that you put the test charge? So what we're looking for is E. And what is E? Force divided by the test charge, Q prime. So that would be 0.600 newtons divided by 3.00 times 10 to the -5 coulombs. That looks like a pretty large field to me, okay? So someone do that on your calculator, and you'll find a huge number. It's going to be a 2, okay? This will be 2 times 10 to the -1 divided by, or 6 times 10 to the -1 divided by 3 times 10 to the -5. That will be 2.00 times 10 to the 4th, maybe? I believe that's right. Now, we don't have a unit for, good deal, thank you. We don't have a special unit for field like we do for force. So we call this a Newton per Coulomb. Newton per Coulomb. There it is. Okay? And that's what we measure fields by. Newton per Coulomb. And that's exactly what they got. Okay. Interesting little thing. They have a blurb here on lightning safety, and they say the proper position to take if one is not able to get inside during a thunderstorm. Notice where he didn't run to get to. The trees. Don't go under a tree during a thunderstorm. They actually can draw the lightning. And if I were him, I would get on the edge of the sand pit. I would get in the lowest part of the sand pit. Maybe that's where he is. I don't know. The lowest part that you can get to. Okay? And get down. And why cover the ears? If the lightning is striking fast, close, it's going to be enormously loud. So to protect your eardrum, do that. And that finished 17.4. There are some odd number exercises 1 through 7 at the end of 17.4. Okay, you think we have enough time to get started on 17.5? I don't think so. So we'll start there next time. Okay, it's exactly where we started the last time I taught the course, so we'll get started there. Any questions? Okay, and let me just do a little bit of a reminder here. I should have done this before anyone left. There's still two people, one withdrew, who has not turned in test 1. Second? Well, at least one is sometime. Test 2, there's 2 different people who haven't turned that in, or one's different anyway. And test 3, I've only gotten 3 in. So let's start getting these in, because it's not going to be too much longer, because you're going till you have test 5. You already have test 4. So don't get too far behind in these. Okay? Good deal. Seems like we're almost saying this. 2 days ago I said have a good happy 4th of July, and now I'll say have a good weekend. And of course working on physics problems will make it good, won't it? Yeah. Of course, yes. Good deal. Any further questions before I shut it down?